Types of energy and their equations, part 2. All right, so for this problem, it says a cart with a mass of 0.25 kilograms is launched up a hill using a spring with a spring constant of 150 newtons per meter. The original length of the spring was 0.08 meters and is compressed to a length of 0.03 meters. The cart starts at a height of 0 meters, and H1 is when the cart is at a height of 0.04 meters. All right, so we are going to do an energy table problem where we are going to identify heights and velocities and energies at these 4 different positions. So the first thing that we need to do is we are going to start with identifying just what types of energies there are at each of these 4 positions. So the steps that we're going to take, we're going to start with 1, which is identify when certain types of energy are 0 and put the zeros in the table. First, what I'm going to do is identify the 3 types of energies for each of the 4 positions. So the first thing we want to identify is spring potential energy. And the only time that there's energy stored in the spring is when a spring is compressed or stretched. So in this first part, this is where your spring is compressed. So you do have spring potential energy. So I'm going to just say yes. In the second one, the spring is no longer compressed. And the same thing for the third and fourth. And so because the spring is not compressed, our spring potential energy will be 0 for each of those. Next, we're going to identify where there's kinetic energy. Kinetic energy is the energy stored in an object. So an object will have kinetic energy if it's moving. So in the first one, it's not moving. That's what this red dot means. So if it's not moving, that means our kinetic energy is 0. In the second one, it is going fast. That's what the big arrow means. That means it's going fast. So yes, there is kinetic energy. At this position, it's also still moving. So there is still kinetic energy. And at the top, it's not moving. Now, one thing to remember is if it was still moving up, then it's not at the highest point yet. So at the very top, that is when your velocity will be 0, and that's why your kinetic energy will be 0 there. And the third one is gravitational potential energy. Gravitational potential energy is the energy an object has because of how high up it is. So I'm going to start with the car at a height of 0. So that means that this first cart does not have any gravitational potential energy. Because if you remember, gravitational potential energy is your mass times gravitational field strength times height. And so when H is 0, any number times 0 will just be 0. So the first one's 0, the second one is also 0. Because the starting height is still 0, it's still at a height of 0. But you will have gravitational potential energy for these last 2. All right, so step 1 of these is to then go ahead and put the zeros in the table. And I also want to talk about what we expect to have happen in terms of our pie charts. So the first one, there's no kinetic energy or gravitational potential energy. That means the whole thing is spring potential energy. In the second one, our spring potential energy is 0 and our gravitational potential energy is 0. So that means the only thing we're left with is kinetic energy. So that means that this whole thing must be kinetic energy. In the third one, we have both kinetic energy and gravitational potential energy. And I could have made it more gravitational potential or more kinetic at this point in the problem. I don't know which one's going to be more. I just didn't want to divide it half and half because I don't want to forget that they are different or that they could be different because I don't know if it's halfway to the maximum height or not. If it's halfway up, then it will be divided half and half. If you divided it half and half, that's fine. Just make sure that when you're doing the table problem later, you don't think that it has to be half and half. And then the last one is all gravitational potential energy because it's not moving and there's no spring potential energy. Alrighty, so now we just need to put these zeros into the table. So when the spring is compressed, our kinetic energy and our gravitational potential energy were 0. For the second one, the spring and gravitational potential energies were 0. In the third one, only the spring was 0. And in the fourth one, kinetic and spring were 0. All right, so that's part 1. Now that we have the zeros in the table, we're going to calculate the energies that we know. For example, finding gravitational potential energy, spring potential energy, anything like that where we have numbers. And just so you know, when I do these problems on the answer keys, I'm trying to go in color order. This year, I'm starting with trying to do step 1 in red and step 2 in yellow and things like that. But if you look at previous answer keys, I am trying to go in color order so that way, as you look at the table, you know what I did first, just kind of to help you out. All right, so there's 2 things that we know. One, we have a height here. And if we have height, that means that we can find gravitational potential energy, because gravitational potential energy is mass times g times height. So in this problem, the mass is 0.25 kilograms. So that means my gravitational potential energy is going to be 0.25 kilograms times 9.8, because we're on Earth, times the height of 0.04 meters. So then our gravitational potential energy will be 0.098. Alrighty, so now we need to find the spring potential energy because we are given information that we need for that. So what I went ahead and did is drew the spring. So it said the original length of the spring is 0.08, and when the spring is compressed, it's a length of 0.03. X, when we do the spring potential energy equation, is going to be the difference between these. So X is the change in length, because that is going to be what determines how much energy there is. Not the original length of the spring, not the final length of the spring, but the difference. So how much it got squished. And our spring potential energy equation, so that's 1/2 times the spring constant times x squared. So this spring constant, or K, and notice that is little k, that's not big K, that's a little k. That spring constant is how strong the spring is. So if it has a really big number for the spring constant, it means it's really hard to compress. Think about like the shocks on your car. If it's a small number, think about like the little tiny springs that are in a pen or mechanical pencil, where you can squish them. And so that spring constant in this case is given to us, and it was 150 newtons per meter. That means that it would take 150 newtons to compress this spring a distance of 1 meter. All right, so now all I need to do is plug in these numbers, but I also realized, oh my goodness, I didn't actually figure out what X was. So X is the difference between the 0.08 and 0.03. So if I subtract the 2, I get an X, or a distance of the compression, as 0.05. All right, so now I'm going to plug these numbers in to my equation. And just as a note, only the X is squared, not the whole thing. So it's just X squared. And so you get a spring potential energy of 0.1875, and the units for that are joules. You can include them or not, that's fine. And so that will go into the table over here, because that's the spring potential energy that you started with. All right, so that's everything that we know so far. So now what we need to do is go on to step 3. In step 3, it says find the total energy and then fill in the total energy for all the rows. So the total energy here is really actually quite easy. So you're going to only look at the energy. Don't add height and velocity. Those are not energy. Only gravitational potential energy, spring potential energy, and kinetic energy are the only 3 types of energy that we are going to be looking at. And to get the total, we need to add the 3 types of energy together to get the total energy. And so all of these rows need to be equal to the total. So now if we look at each of these rows, we need to find one that is only missing one thing, and that is going to be this row right here. So we're going to look at it and go, 0 plus 0.1875 is equal to 0.1875. Now, if you remember, energy cannot be created or destroyed. So if that's my total energy for the first row, that also means that if I have to keep the same amount of energy, then that means that my next row is also 0.1875. And the third row is also 0.1875. And the fourth row is still 0.1875 because the energy cannot be gained or lost without doing work on the system. So we have conservation of energy, so we have to keep the same amount. Now we go to the next step. It says using total energy and the energies from step 2, find the other missing energies. So for this, we just need to think about how each of these rows, we need to make it add up to the total energy. So that means for this one, we have 0 plus whatever this box is, plus 0 needs to be equal to the 0.1875. So that means that this number must be 0.1875. And the same thing has to be true for the third row. But now we've got a number there. So what I'm going to think is, okay, so this is 0.098 plus whatever this box is, plus the 0 has to be equal to 0.1875. So if I plug this into a calculator, then I'm going to just subtract the 0.098 from both sides, and I get 0.0895. And again, the bottom row, something plus 0 has to equal 0.1875. So then this is also 0.1875. All right, and that does it for finding the energy. So now the only thing we have left to do is find heights and velocities. So step 5 is solve for heights and velocities using the energy from step 4. Alrighty, well, kinetic energy is equal to 1/2 times my mass times velocity squared. And gravitational potential energy is m times gravitational field strength times height. So all we need to do is take the energy and use that to solve for height or use it to solve for velocity. Instead of using those things to solve for the energy, we're using the energy to solve for the things. So one that we're going to start with here is we're going to find the highest point. So when we're talking about the highest point and the height, we need to use the equation that has height in it, which is gravitational potential energy. So gravitational potential energy is mass times my gravitational field strength times height. And in this case, my gravitational potential energy is 0.1875. My mass is 0.25, G is 9.8, and the height is what we're solving for. So we're going to just leave the height as H. Now my recommendation here is to take these two numbers, multiply them together first before dividing it to the other side. Students are much less likely to make calculator mistakes if you do that multiplication first. And so you get 0.1875 is equal to 2.45 times my height. And now it's because it's multiplication, we're going to have to do the opposite, which is division. So you will divide both sides by 2.45 because we're trying to get that to cancel out so that H is left by itself. And so we end up with a height of 0.0765. So that number will go right in here for height. And then we just need to find velocities. So using kinetic energy, we're going to find velocity. So the equation for kinetic energy is 1/2 mv squared. And we are going to use this second row here. So here's my kinetic energy. My kinetic energy is 0.1875. So that's why I went ahead and plugged that in here. The mass is 0.25. That's where that came from. And then we just need to solve for velocity. So just the same as the last one, we're going to multiply the 1/2 times the 0.25 first. Because you're going to be way less likely to make a mistake if you do that. So we end up with 0.1875. And it does seem a little bit silly to make you guys write that line down, and it is up to you, but I will tell you in 12 years of teaching that if you do not want to get wrong answers, I very, very highly recommend multiplying 1/2 times your mass before doing anything else and just write it down. That step of writing that down, you are going to make way fewer mistakes, especially in your calculator. So please take that advice. And then you'll divide both sides by the 0.125. And then the opposite of square is square root. So you get 1.2247 is your velocity. So you could just, oops. So you get about 1.22 meters per second for your velocity. All right, so then this goes into that spot. And that is your fastest velocity that you'll have. And then we're going to do the next one. And we're going to do it exactly the same way. So I encourage you, pause the video, try to do it yourself, and then check your answer. You can always just skip forwards in the video. All right, so we're going to do kinetic energy is equal to 1/2 times my mass times velocity squared. In this case, for this next row here, our kinetic energy is 0.0895. So I go ahead and plug it in, and then I multiply the 1/2 times the 0.25, and I get 0.125. I move the 0.125 to the other side, and then I just need to square root to get rid of the square. And I get a velocity of 0.846, and that'll go into this box, 0.846. And last but not least, we have this very last box right here. But that one's actually pretty easy because your kinetic energy is 0. So if you do not have kinetic energy, that means you are not moving. So then this is 0. Let me know if you have any questions.